In today's video, we'll prove why the limit of sine theta over theta becomes 1 as theta approaches 0 using geometric reasoning. This limit is essential for proving the derivatives of trigonometric functions, which we'll cover in the future, and it serves as a foundation for various other formulas as well. Here, you can see a green right triangle with a base length of 1 and a left angle of theta. Right above it, I'll place a pink sector with a radius of 1 and an angle of theta. Lastly, I'll place a yellow isosceles triangle with a side length of 1 and also an angle of theta on top of them. When you separate them like this, we can see that the area of the shape on the right is the largest, followed by the one in the middle, and then the one on the left. Now let's find the area of the smallest yellow isosceles triangle on the left. To find the area of this triangle, let's consider the right triangle formed by separating only the right angle triangle on the left. In this right triangle, we can use the relationship sine theta equals opposite over hypotenuse, which gives us h over 1 and ultimately h. Therefore, the height h of this triangle is equal to sine theta. Now, the triangle with a base of 1 and a height of sine theta has an area of half times 1 times sine theta, which simplifies to sine theta over 2. The area of the first shape has been determined to be sine theta over 2. Now let's proceed to find the area of the next shape. The area of the second shape, the pink sector, can be found by considering it as a portion of a circle with a radius of 1. Since the sector occupies an angle of theta out of total 2 pi radians, we can find the area by calculating the ratio of the theta to 2 pi. And multiplying it by the area of a whole circle. Therefore, the area of sector is given by pi r squared theta over 2 pi, which simplifies to r squared theta over 2 after cancelling out pi in the numerator and denominator. Since the radius is 1, substituting r with 1 simplifies the expression to theta over 2. Hence, the area of pink sector is simply theta over 2. Let's now consider the last shape, the green right-angled triangle. We will denote the height of this triangle as y and use the tangent function to relate it to the angle theta. Using tangent theta is opposite over adjacent, we find that y over 1 equals tangent theta, so y is equal to tangent theta. Therefore, the area of a triangle is given by multiplying half the base length, which is 1, by the height, tangent theta, resulting in an area of tangent theta over 2. The area of the third shape is indeed tangent theta over 2. As shown in the figures above, the areas of the three shapes we calculated satisfy the same inequality as depicted on the screen. For the sake of calculation, let's bring back the inequality. Multiplying both sides by 2 and eliminate the denominators, we can simplify it as follows. Additionally, we'll replace tangent theta on the right side with the sine theta over cosine theta. Then we will multiply both sides by 1 over sine theta to eliminate sine theta terms on the left and right sides. By multiplying all three terms by 1 over sine theta, the left side becomes 1, and the middle term becomes theta over sine theta, and the right side becomes 1 over cosine theta. Now let's take a brief look at a simple example together. We know that the numbers 1, 2, and 3 satisfy this inequality. What if we take the reciprocals of these positive numbers? In that case, the direction of the inequality should be reversed. Just like the example I shown to you, if we take the reciprocals of this inequality, it should become 1 over 1 sine theta over theta and cosine theta over 1 with the reverse direction of inequality. If we simplify the expression by removing the denominator of 1, we have 1 sine theta over theta and cosine theta respectively. Now let's apply the limit to each term of the obtained inequality, considering the condition that theta approaches 0. The limit of 1 on the left-hand side will always be 1, regardless of the value of theta. And as theta approaches 0, the cosine function, cosine theta, converges to 1. Since both the left-hand side and the right-hand side has become 1, the intermediate term, the limit of sine theta over theta, also becomes 1. In today's video, we demonstrated why the limit of sine theta over theta becomes 1 as theta approaches 0. Using this result, We'll proceed to prove the differentiation of trigonometric functions using first principles in the next video. I will continue to create and share informative videos for all of you, so I kindly ask for your continued support and interest. If today's video was helpful to you, please consider subscribing and liking the video. I look forward to seeing you all in the next video. Thanks for watching. This has been your Math Guardian, Alex.